November 8, 1943. Luftwaffe Technical Testing Center, Rechlin, Eastern Germany. Morning frost clung to the grass airfield as a column of military trucks approached Hangar 7, their exhaust forming white plumes in the cold air. Inside the hangar, beneath harsh electric lights that hummed and flickered, sat the reason for the early assembly. A captured American Republic P-47 Thunderbolt, belly-landed in a Belgian field 3 weeks prior and transported to Germany with unusual urgency. The aircraft dominated the hangar floor like a beached whale, massive and incongruous, its unpainted aluminum skin reflecting the overhead lights in harsh geometric patterns. Chief Engineer Klaus Hartmann stood before the fighter, coffee cup forgotten in his hand, staring at the engine cowling that seemed impossibly large for a single-seat fighter. Around him, a team of Luftwaffe engineers and Daimler-Benz technical specialists gathered with notebooks and measuring instruments, their breath visible in the unheated hangar. They had come to understand what they were facing in the skies over Europe, why American fighters were suddenly appearing at altitudes the Luftwaffe considered safe, why they could chase down German aircraft in dives that should have been impossible, why they absorbed damage that would destroy a Messerschmitt and kept flying. The answer sat before them, housed in that enormous cowling. And when they finally opened it and saw what the Americans had built, the war changed for them in ways that had nothing to do with tactics or courage. The P-47 Thunderbolt had appeared over European skies in spring 1943, and German pilots had initially dismissed it as another American design that prioritized size over performance. Early combat reports described a fighter that seemed bloated, heavy, sluggish in turns compared to the nimble Bf-109 or Fw-190. Luftwaffe pilots, veterans of years of combat, assumed they understood this new opponent. Another mediocre aircraft from a nation that built quantity over quality. Formidable, perhaps in numbers, but vulnerable to German skill and superior engineering. They attacked Thunderbolts with confidence, expecting easy kills. What they encountered instead defied their understanding of aerial combat. The P-47's absorbed cannon hits that should have been fatal. 20mm shells that punched through wings and fuselage, leaving holes the size of dinner plates, yet the American fighters kept flying. German pilots watched their ammunition count down to 0 as they poured fire into Thunderbolts that refused to fall, that simply absorbed the punishment and continued fighting. Worse, when the Americans chose to dive away from combat, German fighters couldn't follow. The P-47s accelerated in their dives to speeds that made pursuit suicidal, simply pulling away from their attackers as if the laws of physics operated differently for American aircraft. And at high altitude, above 25,000 feet, where German engines gasped for air and performance deteriorated, the Thunderbolts seemed to grow stronger, climbing and maneuvering with power that shouldn't have been possible in the thin air. Within months, Luftwaffe pilots had learned to treat P-47s with wary respect. These were not easy kills. These were machines that operated by different rules. German intelligence had been collecting data, interviewing pilots, analyzing gun camera footage, trying to understand what made the Thunderbolt so formidable. The numbers they compiled told a story that seemed impossible. The P-47 weighed over 13,000 pounds fully loaded, nearly twice the weight of a Bf-109. It was powered by a single radial engine, a design German engineers associated with bombers and transport aircraft, not high-performance fighters. Yet somehow, this massive, heavy aircraft, using an allegedly inferior engine design, could outrun, outclimb, and outdive Germany's best fighters at altitude. The logical conclusion was that American pilots were simply better trained, more numerous, more willing to use hit-and-run tactics rather than engage in traditional dogfights. But the pilots who had fought them knew better. They had seen Thunderbolts sustain damage that would destroy any German fighter. They had watched American pilots make tactical choices that suggested absolute confidence in their aircraft's performance, diving away at full throttle, climbing to altitudes where combat shouldn't be possible, absorbing fire that should have been lethal, and pressing their attacks anyway. The Thunderbolt wasn't just another fighter. It was something different. And when the captured example arrived at Rechlin in October 1943, bearing the scars of combat and a belly landing but essentially intact, German engineers finally had the opportunity to understand what they were facing. What they discovered in that cold November hangar would reshape German aviation doctrine. Not because it suggested new possibilities, but because it revealed limitations the Luftwaffe could never overcome. The investigation began with external measurements and documentation. Teams photographed the aircraft from every angle, measured dimensions, weighed components, assessed structural design. The Thunderbolt's size was immediately apparent. It was enormous for a single-seat fighter, its fuselage nearly as large as a medium bomber's. The wings were thick, almost stubby, yet they housed 8 50-caliber machine guns and ammunition for over 400 rounds per gun. The landing gear was massive, suggesting the aircraft had been designed to handle extraordinary weights and hard landings. But the real revelation came when engineers removed the engine cowling panels and exposed what lay beneath. The Pratt & Whitney R2800 Double Wasp engine filled the entire front section of the aircraft like a mechanical heart. 18 cylinders arranged in 2 radial rows, each cylinder head the size of a man's fist, cooling fins machined with precision that suggested automated manufacturing rather than hand-fitting. The engine's displacement was 46 liters, nearly 3 times larger than the Daimler-Benz DB605 that powered the Bf109. But size alone didn't account for the performance. What stunned the German engineers was the supercharger installation. Mounted behind the pilot, connected to the engine by ducting that ran underneath the cockpit, sat a General Electric turbo supercharger the size of a beer keg. This wasn't the mechanically driven supercharger used in German engines, powered by the crankshaft and bleeding horsepower to compress intake air. This was an exhaust-driven turbocharger that used waste gases, energy that would otherwise be lost, to spin a turbine at speeds exceeding 20,000 RPM, compressing air to sea-level density even at 30,000 feet altitude. The Americans had solved the fundamental problem of high-altitude performance not by building a bigger engine, but by building a system that maintained engine power regardless of altitude. Hartmann had stood beside the exposed engine for nearly an hour, tracing the ducting with his eyes, understanding the implications. At sea level, the R2800 produced approximately 2,000 horsepower, already more than any German fighter engine. But where German engines lost power as altitude increased and air thinned, the Thunderbolt's turbocharged system maintained nearly full power up to 25,000 feet and beyond. This explained everything the pilots had reported. The Thunderbolt could climb to altitudes where German fighters struggled, then fight at full power while the Luftwaffe gasped. It could dive at speeds that would tear wings off German aircraft because its massive engine and heavy structure provided stability. It could absorb incredible damage because American engineers had surrounded the pilot and critical systems with armor and redundant controls, accepting the weight penalty because the engine had power to spare. The P-47 wasn't designed to turn with a Bf-109. It was designed to dominate at altitude,
to escort bombers into the heart of Germany, to absorb flak and fighter attacks and bring its pilot home. And it succeeded because American engineers had approached the problem differently than their German counterparts. Where Germany built lightweight fighters optimized for performance, America built a fighter optimized for mission success and gave it an engine powerful enough to overcome any weight penalty. The investigation continued for weeks as teams disassembled the Thunderbolt piece by piece, documenting every component, every system, every design choice. The engineering philosophy visible in the aircraft's construction told a story as significant as the performance numbers. The R-2800 engine showed evidence of mass production techniques, precision castings, standardized components, tolerances that suggested automated machining rather than hand-fitting. The cylinders were identical, interchangeable, manufactured to specifications so precise that any cylinder could replace any other without custom fitting. The cooling fins were machined, not hand-filed. The connecting rods were forged to identical weight, requiring no individual balancing. Every aspect of the engine spoke to manufacturing systems designed for volume production while maintaining quality. German engineers examining the workmanship recognized craftsmanship that equaled their own, but applied at scales they couldn't match. Daimler-Benz built excellent engines through careful hand assembly by skilled workers. Pratt & Whitney built excellent engines on production lines that delivered hundreds per month. The philosophical difference was stark. German aviation had been built on the assumption that quality required individual attention, that superior performance came from careful optimization of each aircraft. American aviation had learned to engineer quality into the production system itself, to design for manufacturing, to achieve consistency through process rather than through craftsmen. The turbo-supercharger represented technology that Germany had explored, but never perfected. German engineers understood the principles: use exhaust gases to drive a compressor, recover waste energy, maintain power at altitude. But implementing those principles in a reliable production-ready system had proven elusive. Turbochargers required exotic materials that could withstand exhaust temperatures exceeding 1,500 degrees Fahrenheit. They required precision bearings that could survive sustained operation at extreme RPM while exposed to corrosive exhaust gases. They required control systems that could regulate boost pressure automatically as altitude changed, preventing overboost at low altitude or underperformance at high altitude. Germany's few experimental turbocharged engines had suffered from chronic reliability problems: bearings that failed after hours of operation, turbine wheels that cracked under thermal stress, control systems that couldn't maintain stable operation. The systems worked in laboratory conditions, but failed in combat, where temperature extremes, sustained high-power operation, and lack of maintenance destroyed components faster than they could be replaced. General Electric's turbo-supercharger, by contrast, was production-ready technology that had been refined through years of development and testing. It was designed for ease of maintenance, used readily available materials, incorporated safety systems that protected against operator error or combat damage. The Americans had solved problems that German engineers were still struggling with, not through superior theoretical understanding, but through superior development processes, extensive testing, and willingness to invest resources in perfecting a technology before deploying it. The weight of the Thunderbolt had initially puzzled German analysts. Why build a fighter so heavy when additional weight degraded performance? The answer became clear as teams mapped the aircraft's structure and systems. The P-47 carried armor protection that would have been considered excessive in German fighters. Thick steel plates behind the pilot, armored glass in the windscreen, self-sealing fuel tanks that could absorb multiple hits without catching fire. The airframe itself was massively overbuilt by German standards, using structural members sized for loads far exceeding normal flight stresses. American engineers had designed the aircraft to survive, to bring its pilot home despite battle damage, to operate from rough forward airfields without structural failure, to absorb the stresses of sustained high-speed flight and repeated high-G maneuvers. This represented a different philosophy of fighter design. German fighters prioritized performance, accepting vulnerability as the price of superior maneuverability and speed. The P-47 prioritized survivability, using brute engine power to overcome the weight penalty of protection. The approach worked because American industry could produce engines powerful enough to make it viable. A 2,000 horsepower engine allowed design choices that a 1,200 horsepower engine made impossible. The Americans hadn't just built a more powerful engine, they had used that power to fundamentally rethink what a fighter could be.
Hartmann's final report to the Reich Aviation Ministry, submitted in December 1943, filled over 200 pages with technical analysis, performance projections, and strategic assessments. The conclusion was stark and unavoidable. Germany could not match the P-47's performance with existing technology or industrial capacity. The R-2800 engine represented an investment in development, tooling, and production infrastructure that Germany simply couldn't replicate while simultaneously fighting a war on multiple fronts. Daimler-Benz and Junkers could theoretically design equivalent engines, but bringing them from concept to production-ready systems would require years and resources Germany didn't have. The turbo-supercharger technology required materials and manufacturing capabilities beyond current German capacity. Even if Germany could somehow produce equivalent engines, the Luftwaffe lacked the fuel supplies to operate them. The R-2800 engine consumed fuel at rates that would exhaust German aviation gasoline reserves in months. The report didn't recommend attempting to copy the Thunderbolt or develop equivalent aircraft. Instead, it acknowledged a fundamental shift in the air war's balance. American fighters could now operate at altitudes and with performance margins that negated German tactical advantages. The Luftwaffe would have to adapt tactics, avoid combat when possible, focus on aircraft that German industry could actually produce in meaningful numbers. The era of German air superiority, built on superior training and performance, was ending. The era of American industrial dominance was beginning. The psychological impact on Luftwaffe engineers and pilots who learned of the investigation's findings was profound and demoralizing. For years, German aviation had operated under the assumption that German engineering represented the pinnacle of aircraft design, that Messerschmitts and Focke-Wulfs were the best fighters in the world, limited only by numbers and fuel rather than capability. The Thunderbolt shattered that assumption. Here was an American aircraft that outperformed German fighters in most flight regimes, that survived damage German fighters couldn't withstand, that operated at altitudes where German fighters barely functioned. And it achieved this not through revolutionary technology or brilliant design breakthroughs, but through systematic engineering and massive industrial investment. The R-2800 engine wasn't a miracle, it was the product of years of development, extensive testing, generous funding, and production systems optimized for quality at scale. German engineers recognized excellence when they saw it, and what they saw in the dismantled Thunderbolt was excellence they couldn't match. Not because German engineers lacked skill or knowledge, but because German industry lacked the resources and infrastructure to implement that knowledge at the scales necessary for modern air warfare.
The realization that superior engineering alone couldn't overcome industrial disparity was bitter medicine for men who had built their careers on technical excellence. German pilots who flew captured Thunderbolts, several examples had been restored to flight status for evaluation, reported experiences that confirmed the engineers' analysis and deepened their understanding of what they faced. At low altitude, the P-47 handled like a truck, heavy, sluggish, easily outmaneuvered by lighter German fighters. But climbing above 20,000 feet, the aircraft transformed. Where German fighters felt increasingly lethargic as air thinned, the Thunderbolt maintained power and responsiveness. The engine note remained steady, the controls stayed responsive, the rate of climb barely decreased. Test pilots pushed the aircraft through maneuvers at 28,000 feet that would have been impossible in a Bf-109 at the same altitude. They dove the Thunderbolt past 500 miles per hour, speeds that would cause control flutter and structural failure in German fighters, and found it stable and controllable. They deliberately damaged test aircraft to assess survivability, shooting holes in wings and fuselage, and discovered that the Thunderbolt continued flying with damage that would have been catastrophic in German designs. One test pilot, comparing the P-47 to the FW-190, wrote in his report, "The American aircraft lacks the agility and elegance of German fighters, but it operates in a different paradigm. It doesn't seek to outmaneuver opponents. It seeks to outlast them, outclimb them, and bring overwhelming firepower to bear from positions they cannot reach." Against properly flown Thunderbolts at altitude, German fighters are at a fundamental disadvantage no amount of pilot skill can overcome. The strategic extensions extended far beyond individual aircraft performance. By late 1943, American heavy bomber formations striking German targets were increasingly escorted by P-47s capable of protecting them throughout their missions. Where previously German fighters could attack bomber formations with relative impunity, exploiting the brief windows when fighters had to break off due to fuel constraints, the Thunderbolt's long-range and drop-tank capability meant American fighters could now escort bombers deep into German territory. The Luftwaffe faced a choice: engage the escorts and suffer losses, or avoid combat and allow bombers to strike unhindered. Neither option was sustainable. Engaging P-47s at high altitude meant fighting at a disadvantage, accepting losses to aircraft and experienced pilots Germany couldn't replace. Avoiding combat meant allowing unchallenged bomber strikes that destroyed German industrial capacity. The Thunderbolt's appearance marked the beginning of the end of effective German air defense. Not because German pilots lacked courage or skill, but because they lacked aircraft capable of fighting on equal terms. The industrial and technological gap had become a yawning chasm that tactics and determination couldn't bridge. German aviation was fighting the war Germany could afford to fight, building fighters with limited resources, using engines that required less strategic materials, training pilots with constrained fuel budgets that would have sustained the entire Luftwaffe for months.
The R-2800 engine became a recurring symbol in German aviation discussions throughout 1944 and 1945, shorthand for American industrial capacity, for the resource disparity that defined the war, for the futility of matching American production. When German engineers proposed new aircraft designs, the question always arose, but what engine would power it? Germany's most advanced engine projects, the Junkers Umo 213, the Daimler-Benz DB603, produced 13 to 1,500 horsepower, impressive for their displacement, but still far below the 2,000 horsepower Americans achieved with the R2800. And the American engine was in mass production, delivered by the thousands, while German engines remained constrained by material shortages and manufacturing bottlenecks. The disparity wasn't limited to power output. American engines demonstrated reliability that German engines couldn't match. The R2800 operated for hundreds of hours between overhauls. German engines required constant maintenance, suffered from chronic cooling problems, broke down at rates that left aircraft grounded despite being structurally intact. American aircrew reported engine reliability so high they rarely thought about mechanical failure. German pilots flew with the expectation that engines might fail at any moment, that overheating or bearing failure or any of dozens of mechanical problems might force emergency landings. The reliability gap reflected differences in materials quality, manufacturing precision, and design maturity, all areas where German industry was struggling while American industry thrived. Hartmann had visited Daimler-Benz manufacturing facilities in early 1944, hoping to discuss potential responses to American engine technology. What he found confirmed his worst fears. The factory floors showed the strain of years of war production, skilled workers drafted into military service and replaced with forced labor, machine tools worn beyond specification and irreplaceable, materials substituted with inferior alternatives because proper materials were unavailable. Engineers described development projects constrained by lack of testing resources, lack of strategic materials for prototypes, lack of time to properly refine designs before production demands forced them into service. The contrast with what Hartmann had seen in the captured Thunderbolt was stark. American components showed evidence of unlimited access to high-grade materials, extensive testing, manufacturing processes optimized for quality. German components showed evidence of constant compromise, good enough to work, never as good as design specified, always limited by what was available rather than what was optimal. The industrial base that had made Germany's early war success possible was crumbling under years of sustained combat, strategic bombing, and resource constraints. Meanwhile, American industrial capacity was reaching its peak, producing not just aircraft and engines, but the entire supply chain: fuel, ammunition, spare parts, training aircraft, everything necessary to sustain air operations at scales Germany could only imagine.
The younger engineers, the ones who hadn't known pre-war Germany, were the most affected by the Thunderbolt investigation. They had grown up believing in German technical superiority, in the myth of Germanic engineering excellence that would overcome any obstacle. The R2800 engine shattered that myth by demonstrating that excellence wasn't enough, that resource availability, industrial infrastructure, and manufacturing philosophy mattered as much as engineering skill. Some of these younger men would survive the war and carry these lessons into Germany's post-war reconstruction, applying them to rebuild German industry with new understanding of what made nations powerful in the industrial age. But in 1944, standing in the Rechlin hangar, looking at the dismantled Thunderbolt, they simply felt the weight of realization that they were fighting for a nation that had challenged an opponent it fundamentally misunderstood, that had assumed courage and quality could overcome quantity and resources, that had learned too late that modern warfare was decided in factories as much as on battlefields. By mid-1944, the skies over Germany filled with Thunderbolts, their distinctive profiles recognizable to Luftwaffe pilots who had learned to regard them with wary respect. The massive radial engine sound became familiar, a deep, powerful drone that announced American presence at altitudes German fighters struggled to reach. Young German pilots rushed through abbreviated training with insufficient fuel for proper preparation, climbed to meet them, and discovered what veterans already knew. Engaging P-47's at altitude was nearly suicidal. The American fighters held every advantage: altitude, speed, firepower, protection. German pilots watched their attacks bounce off armored American aircraft, watched their ammunition exhausted without decisive results, watched Thunderbolts simply accelerate away when combat turned unfavorable. Some pilots reported feeling hunted rather than hunting, pursued by enemies who held all the advantages and pressed them relentlessly. The psychological burden of fighting from permanent disadvantage wore down morale as surely as combat losses wore down force strength. Pilots who had expected to defend the fatherland with skill and courage found themselves defending it with desperation and hope, knowing that each mission might end with a thunderbolt on their tail, diving faster than they could escape, firing 8 heavy machine guns they couldn't evade. The symbolic weight of the R-2800 engine extended beyond its technical specifications. In German military culture, which valued discipline, skill, and quality craftsmanship, the engine represented a different philosophy: victory through abundance rather than excellence, through overwhelming resources rather than superior ability. American pilots flying Thunderbolts didn't need to be as skilled as Luftwaffe veterans. They just needed adequate training and a willingness to leverage their aircraft's advantages. The P-47 forgave mistakes German fighters punished, absorbed damage German fighters couldn't survive, maintained performance in conditions where German fighters struggled. This removal of human factors from combat, this reduction of air warfare to contests of industrial capacity rather than individual skill, violated something fundamental in German military thought. The Luftwaffe had been built on the assumption that superior training and aircraft quality could overcome numerical disadvantage, that a well-trained German fighter in an excellent German fighter was worth several enemy pilots in inferior aircraft. The Thunderbolt proved that assumption obsolete. An adequately trained American pilot in an aircraft backed by vast industrial resources could dominate a veteran German pilot constrained by fuel shortages, material limitations, and aircraft that couldn't match American performance.
The final reports from the Rechlin investigation, classified and distributed only to senior Luftwaffe commanders and aviation ministry officials, concluded with assessments that read like obituaries for German air power. The technical analysis was comprehensive and damning. Germany could not match American engine technology, could not replicate American manufacturing systems, could not compete in the resource-intensive domains where air superiority would be decided. The strategic analysis was equally bleak. American fighters would continue improving, while German fighters stagnated, constrained by industrial limitations that would only worsen as bombing destroyed factories and resource shortages deepened. The recommendations were limited to tactical adaptations and realistic assessments of what German aviation could still achieve: defending critical targets when possible, avoiding combat when advantageous, conserving experienced pilots for missions that mattered. There was no path to victory described in these reports, no technological solution proposed that might reverse German fortunes. Just cold analysis of what the Thunderbolt represented, proof that Germany was fighting an opponent whose industrial capacity operated on a different scale, whose engineering systems produced excellence reliably, whose resource base could support the kind of warfare that Germany could barely sustain. Hartmann would survive the war, his expertise valuable enough to keep him in technical roles rather than combat postings. In the decades after 1945, he would occasionally lecture at engineering schools, using the P-47 investigation as a case study in industrial warfare and manufacturing philosophy. His message was always the same: technical excellence alone doesn't win wars between industrial nations. What matters is the ability to translate excellence into production, to build quality into systems rather than into individual products, to marshal resources at scales that make overwhelming force possible. Germany had possessed excellent engineers, skilled workers, sophisticated theoretical knowledge. But it had lacked the industrial infrastructure, the resource base, and the manufacturing philosophy to compete with American production. The R-2800 engine wasn't just a more powerful engine. It was evidence of an industrial system that could turn theoretical knowledge into reliable products at massive scale, that could invest billions in development and infrastructure, that could sustain production while simultaneously improving designs. Germany's aviation industry never stood a chance against such an opponent, not because German engineers were inferior, but because they operated within constraints American engineers never faced. The dismantled Thunderbolt remained at Rechlin until early 1945, when advancing Soviet forces forced evacuation of the facility. Engineers burned documents, destroyed sensitive research, and abandoned equipment they couldn't transport. The P-47 was left behind, its massive engine still partially disassembled on the hangar floor, components scattered across workbenches, measurement instruments lying beside the systems they had been analyzing. Soviet forces captured the facility in April 1945 and found the aircraft along with notes and reports that told the story of German engineers trying desperately to understand an opponent they couldn't match. The R-2800 engine was eventually shipped to the Soviet Union for analysis, where Soviet engineers drew the same conclusions their German counterparts had reached: that American aviation represented an industrial capability qualitatively different from anything achieved in Europe, that copying individual technologies missed the larger lesson about manufacturing systems and resource allocation. The Thunderbolt's legacy wasn't just its combat record. It was the proof it provided that industrial wars were won by factories working in concert with engineering departments, by nations that could translate wealth into weapons at scales that made tactical excellence irrelevant. November 1943. The frost had melted from the grass outside Hangar 7 as afternoon light slanted through the high windows, illuminating the dismantled Thunderbolt in golden rays that seemed almost reverent. Hartmann stood alone beside the exposed R-2800 engine, coffee cup long since empty, notebook filled with measurements and observations that would form the basis of his final report. He reached out and touched one of the engine's massive cylinders, feeling the precision of the machining, the quality of the materials, the evidence of excellence built at scale. This engine, this single engine that powered one fighter aircraft in a war where thousands of such aircraft were being produced, represented industrial capacity that Germany couldn't match, and power that Germany couldn't replicate. It was a monument to American abundance, cast in aluminum and steel, engineered for reliability rather than economy, built to win through overwhelming force rather than through clever efficiency. The engine was a teacher, offering lessons that arrived too late to save Germany, but clear enough to shape the post-war world. Wars between industrial nations were decided not by who had the best engineers or the bravest soldiers, but by who had the factories, the resources, the industrial systems to translate national wealth into military power.
Excellence in isolation meant nothing. Excellence at scale meant everything. The R-2800 represented excellence at scale. 2,000 horsepower multiplied by thousands of aircraft. Reliability measured in hundreds of hours multiplied by thousands of missions. Industrial might measured not in individual achievement, but in production capacity. And against such abundance, against such systematic application of resources and knowledge, courage and skill and determination were necessary but insufficient. The war had been lost in factories and foundries, in industrial planning and resource allocation, long before the shooting started. The massive engine before him was simply the proof, rendered in metal and oil, of truths Germany had learned too late to matter.